Okay, so actually in previous week we have done this question, okay, but I have done a little mistake there, okay. So to avoid the confusions, okay, I will I'm going to record this session again and I will upload it, okay. Uh, so before doing this question, before working out this question, we will try to do it in general way. Okay. Okay. So you already know that what is AM modulation. Okay. So for the AM amplitude modulation, okay, we use both carrier and baseband signal or information signal. Information signal are both analog. Okay, both are in analog form. Okay. So so we need two signals for the modulation. Okay, one is the RF signal. Okay, RF signal. We are doing the RF modulation here. So we need the RF signal first. Okay, and normally it is referred as carrier signal XCT. Okay, and we should have the message signal or baseband signal. Okay, so this is XT, both are analog. Okay, so we will have the output signal. Okay, output modulated signal XMT. Okay, so in AM modulation, what we are doing, you already know that changing, we are changing the amplitude of the carrier signal XCT carrier signal according to the amplitudes levels of modulating signal or baseband signal. This is also called as modulating signal. Okay, this is called as modulating signal or baseband signal. Okay. Okay, according to the level of modulating signal or baseband signal or information signal or message signal, anything. Okay, so this is the amplitude modulation. We have talked this several times. Okay, so now you need to write the output waveform. Okay, so output waveform will look like this. Okay, so this is the output waveform. You need to remember this. Okay. Okay. So this is the output signal. XMT is equal to AC. Okay, AC. So you already know that this RF signal or carrier signal is normally a sinusoidal signal. Okay. So normally it is a sinusoidal signal because RF signals are sinusoidal in nature. Okay. So we have to get the carrier signal. We have to get the sinusoidal signal as a carrier signal. Okay. So I am assuming my carrier signal is sinusoidal signal. So it is look like this. CT is equal to AC cos omega C T. Okay. So you can add the phase here, but we are not going to change. We are not going to do any changes in the phase. Okay. So you can also avoid this phase. Okay. You can avoid writing this phase here. Okay. So if the RF signal is the carrier signal, okay, the carrier signal, RF signal or carrier signal is a sinusoidal signal, okay, and this is its amplitude, and this is its frequency, angular frequency, angular frequency. It is also can be written as 25 FC. This FC is the normal frequency, okay. So omega C is equal to 25 FC, okay. This thing we have discussed several times, okay. So now XMT is equal to AC, okay, 1 by mu our message signal xt and our carrier signal xct. Okay, so this is the normal expression. Okay, this is the expression for amplitude modulated signal. Okay, so this is the expression for amplitude modulated signal. Okay, and you know that this mu is the modulation index. Okay, modulation index, and it is defined as AM divided by AC. Okay, so this is the modulating signal amplitude, baseband signal amplitude. Okay, XT amplitude. Okay, and this AC is the carrier amplitude, XCT amplitude, carrier signal amplitude. Okay. Uh, okay, now special things you need to remember, remember. Okay, so this XCT means this is the waveform without the amplitude, or the amplitude is 1 here actually. Okay, amplitude is 1 here. This XCT is the signal without the amplitude. Okay, amplitude is 1 here because already amplitude is there. No? So AC XCT. So that is our complete signal. Okay, so actually we can say that this signal is a nominalized to the amplitude. Okay, so this is a nominalized waveform signal. Okay, the signal is divided by the amplitude. Okay, so this XCT is without the amplitude. Okay, without the amplitude. And you know that this so mu is AM divided by AC. Okay, so if you apply this AM divided by AC instead of this mu, okay, instead of this mu, okay, this AM divided by AC, okay, instead of this mu, okay. So you can see that AM XCT, okay. So here the modulating signal, or XT amplitude is there. It is already included in the mu. Okay, so this XT also here, it is also the wave signal without the amplitude. This is the message signal without the amplitude. Okay, message signal without the amplitude. Message signal without the amplitude, or we can say that it is also nominalized signal without the amplitude. Okay, it is divided by the amplitude. Okay, so that is it. Okay, so you should have that idea. Okay, so this is our amplitude modulated time domain signal. Time domain signal, we called it wave. Okay, so this is our wave. Okay, amplitude modulated signal. Okay, now, okay, now for the analytical purpose, okay, so this XT, okay, what is this XT? It is the information signal. This XT is the information signal. Okay, so you know that normally real-time information signals are very complicated. For example, if you consider a voice, it has several frequency components. Okay, like this. Okay, it is not a basic signal, simple signal. Okay, it is very complicated signal. Okay, so normally almost all the information signals are very complicated. So if you use this kind of, these are also random signals. Okay, so if you use this kind of random signal for the to for the analytical purpose, okay, this analysis will be very complicated. Okay, so you can get only one frequency component. You can get only one frequency component. Okay, frequency component as what? As the message signal or modulating signal. Okay. Modulating signal. So what is that one frequency component means? It should be a basic signal. Okay, so it should be a sinusoidal signal. Okay, so if you use a sinusoidal signal as the modulating signal, or information signal as this xt. Okay, so that signal will like this cos omega m. Let's say that this is our information signal. Okay, so you can see that this is a sinusoidal signal, basic signal. Okay, this is sinusoidal signal, basic signal, and only one tone is there. Only one frequency component is there. So we can say that only one tone is there. Okay. So, okay. So I think I have shown you. So you can go to the YouTube and you can check single tone sound. Okay. So you can get a 900, 600 hertz sound. Okay. So it will be a beat sound likewise. Okay. So you can get that single sound. If you need, you can hear. Okay. So it is also sound. Okay. It also generate a sound actually. Okay. It can generate a sound. This one tone can generate a sound. Okay. So if you send through this microphone, it will generate a sound. Okay. So it is information. You can consider it as an information. Okay. So this is our uh, information signal, and we use one tone. Okay. So we call this. Okay. So if we use this signal for the analytical purpose, okay, we call this single tone modulation. Single tone amplitude modulation, because we are going to modulate only one tone. Okay, here we are going to modulate only one tone. Okay, only one tone. That means the sine wave, sinusoidal wave. Okay, so that is the idea. Okay, so so I will get my information signal as am cos omega mt, and my carrier signal is AC cos omega CT. Okay, so what I have to do is I have to apply them to here. Okay, so I have xmt is equal to AC 1 plus mu xt. Okay, and xct. Okay, so if I write in terms of these signals, okay, okay, so it will be like this. SMT is equal to AC. Okay, AC is the carrier amplitude. So I can write it as AC. Okay, 1 plus mu, and this XT should be without the A, without this amplitude. Okay, so it is only cos omega mt. Okay, so without the amplitude. Okay, so it is divided by the amplitude actually. Okay, so we can say that it is a nominalized signal. Okay, or simply without the amplitude. Okay, and this xct also without the amplitude. Okay, so it will be cos omega c. Okay, so this is the general form. Okay, so this is the general form for general form of single tone, one tone, single tone amplitude modulated signal. Okay, signal or waveform, time domain signal waveform. Okay, so you should know this. Okay, so please be careful when you apply, when you uh, substitute xct and xt, you have to substitute it without the amplitude. Okay, okay, so you know that this mu is equal to am divided by s. Okay, so this is the general form. Okay, okay, now I think you can do this one. Okay, type the completed waveform. Okay, only thing you have to apply this mt is the xt actually. Okay, xt, and this is ct is xct. Okay, so you have to type them here. Okay, so now I'm not going to type them. Okay, so you can simply do that. Okay, so that is all. Okay, okay, now so you have to find the power of the carrier signal. Okay, so so we have actually mm, we know that there are some power signal and there are some energy signal. Okay, so there is a procedure to find the power of a signal and energy of a signal. Okay, so those stuff we are learning in signal and system subject. Okay, but some of you haven't done that subject. Okay, so I will take another approach to explain how to find the power of a carrier signal and power of a so we will try to find the power of the carrier signal first. Okay, okay, so how to find the power of the carrier signal? Okay, so you know that carrier signal is a sinusoidal signal. Okay, so let's see. Okay, so here we are going to find the power, find the power of a sinusoidal signal, sinusoidal signal. Okay, sinusoidal signal. Let's take any sinusoidal signal. Any sinusoidal signal. Let's take that YT. Okay, YT. This is any sinusoidal signal. A cos omega t plus phi. Okay, so phase is there also. Okay, now we know that. Okay, let's say that this is a voltage signal. Okay, voltage signal. This is a voltage signal. Okay, so that means the voltage. Okay, if you consider the voltage with respect to time. Okay, so it is changing like this. Okay, it is changing sinusoidally. Okay, so the frequency is omega. Okay, angular frequency is omega and it is equal to pi f. Okay, and the phase is there is some phase difference and that is 5. Okay, and the amplitude is A. Okay, let's say that amplitude is A. Okay, so this is the um, peak voltage. This is the peak voltage and this is the minus peak voltage. Okay, so 2A is the peak to peak value, peak to peak voltage, VPP. Okay, so this A can be any value, 2 volt, 3 volt, 5 volt, any value. So it is measured with volt and this is measured with time. Okay, so you know that if you connect a battery, if you get a battery and if you connect it through a resistor, okay, if you connect it to a resistor, let's say that the voltage across this resistor is V. Okay, the voltage across this resistor is V. Okay, so you know that, so you can find. So let's say that this is a DC current. Okay, so you have a DC value. The V is not changing. Okay, so if you need to find the power dissipated through this um, resistor, okay, dissipated through this resistor, it is, you know that it is equal to VI and also V square by R. Okay, so you know the voltage and you know the resistor. Okay, so power is V square by R. Okay, so you can find the power like this. Okay, now say that you replace this battery with this voltage source. Okay, so here you just put the voltage source here. Okay, so this is not a DC voltage, it is a AC voltage. Okay, so this V is varying. Okay, V is increasing and decreasing like this. Okay, so to find the power, what you have to do? Okay, so here you have the signal and you have to get the RMS value. Okay, so you have to get the VRMS value. Okay, so that is the voltage. If you connect this through a resistor, okay, so this will be dissipating some power. No? Okay, so if you fix a constant voltage source with the VRMS value, it will also dissipate the same value. Okay, so that is the definition of the VRMS. Okay, so I think you already know it. Okay, so anyway, for sinusoidal signal, we know that RMS value is equal to the peak value divided by root, okay, divided by root, okay. So if you want to find the power dissipated through this resistor for this signal, okay, for this sinusoidal signal, so it is equal to nothing but V square divided by, sorry, VRMS square divided by R. Okay. So what is VRMS? It is amplitude divided by 2 square, and it is divided by R. Okay. So it is actually A square divided by 2R. Okay. So this is the power dissipation through a resistor R. Okay. If you send a sinusoidal signal. Okay. So you no need to consider about the frequency, you no need to consider about the phase. Okay. So the power dissipation is only depend on the amplitude. Okay. This is the only dependent variable. Okay. Not the variable, dependent parameter. Okay. So this is the power will be depend only on the amplitude parameter of the signal. Okay. So that is it. Okay. So you know that if you get any sinusoidal signal, if you ask to find the power, okay, so it will be power of a sinusoidal signal is equal to the amplitude square divided by 2R. Okay. So let's say that if you consider this R as 1 mole, this R as 1 mole, okay. So this R actually it is divided by R again. Okay. So that is how it is. We can set it to 1 mole. Okay. In other way, we are going to normalize it to 1 mole. Okay. So if you normalize this to 1 mole, that means if you consider this R as 1 mole, okay. So the say sinusoidal, the power of a sinusoidal signal through 1 ohm resistor, we have A square divided by 2. Okay. And this is we call nominalized power. Nominalized power. Okay. Actually, we are asking to find the nominalized power here. Okay. We are asked to find the nominalized power. Okay. So if you know, so the carrier signal, you know, carrier signal is 50 cos 25 CT. So the power is nothing but A square. So this is the amplitude. Okay. So it is A square divided by 2. Okay. So you can do this one also. Okay. 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 Then how to do this one? Okay. How to do this? Okay. We can, so we will try to write the waveform again. Okay. Okay. So if we write the waveform again, XMT, it is equal to AC1. Okay. So now instead of mu, I will write AM divided by AC. Okay. So here we have cos omega MT. That is our information signal. And here we have cos omega CT. This is our carrier signal, nominalized carrier signal. Okay. So if you expand this, okay, if you expand this, you will have AC cos omega CT. This is multiplied by this one plus AC cancelled, and you have AM. You have here cos omega MT cos omega CT. Okay. So now look at this equation. Okay. So this is a sinusoidal signal. So one frequency component. One frequency component. This is one frequency component. Okay. And you can see that this is we have multiplied these two signals. There are two signals, and we have multiplied. There are two cos signals. We have multiplied. Okay. So there is a multiplication. No? So at once we can't, by looking at, we can't say that how many sinusoidal signal are here. We can't say that. Okay. So if we can can convert this multiplication into addition or subtraction, so we can say that. So we will have separate sinusoidal signal. Okay. So we will have separate frequency component, and also we have separate sinusoidal component. So we can find the power of separate sinusoidal component. Okay. So, so what we have to do is we have to convert this multiplication into a plus or into addition or subtraction. Okay. So for that, uh, you can use your basic trigonometric knowledge. Okay. Actually, you can go through that one also. You can find the power of this signal using a normal way. Okay. Okay, but this one may be much easier. Okay, so you can convert this multiplication into addition. Okay, so there are cosine cos two cos multiplication. Okay, so if there are two cos multiplication, we can use this identity. Okay, so we know this identity. Okay, we already know this identity. We have used them several times. Okay, in level maths also. Okay, so cos alpha plus beta is equal to cos alpha cos beta minus sin alpha sin beta, and you have cos alpha minus beta is equal to cos alpha cos beta plus sin alpha sin beta. Okay, so you can use these two lines. Okay, so if you have sin and cos term, if you have sin and cos term, what is the identity you have to use? So you can use that sin alpha plus beta and sin alpha minus beta. Okay, so you have here sin alpha cos beta plus cos alpha sin beta. Okay, cos alpha sin beta. Okay, and here also you will have sin alpha cos beta minus cos alpha sin beta. Okay, so now for this one we no need to use that term. Okay, so if you have cos and sin terms, you can use this identity and convert it to again for a separate sin and cos term. Okay, using this one. Okay, now we have to use this identity. Okay, so if you add them together, okay, so you can use this, you can see that the sin and sin term cancel out. Okay, and you will have cos alpha cos beta is equal to half cos alpha plus beta plus cos alpha minus beta. Okay, so here also we have cos alpha cos beta terms. Okay, so you can, so it is just like this one. Okay, so you can expand it using this. Okay, so here you can get you can get like this. Okay, so you have it's empty is equal to AC cos omega CT plus, okay, so instead of this cos omega MT cos omega CT, I have replaced this one. Okay, so I have AM here. Okay, and I have this half here, so half, so I have here cos alpha, sorry, cos alpha and beta now omega M and omega C. Okay, so I have cos omega C plus cos omega M plus AM divided by 2. Okay, AM here, AM and divided by 2, and this one cos alpha minus cos beta. That means cos omega C minus cos M, cos omega C minus omega M. Okay. Okay, now you can see that you have separate sinusoidal signal. Okay, now you can find the power here, that is AC square divided by 2, and you can find the power here, so that is AM divided by 2 is square divided by 2, so that means AM is square divided by 8. Okay, and here also you have AM is square divided by 8. Okay, so you can find the power here you can find the power and you can find this power. Okay, so what is the total power? Total power is the addition of all the power. Okay, so you can add all the power. So you have AC square by 2, AM square by 8 plus AM square by 8. Okay, so this is the total power. It is also very easy. You can find. Okay, so this one also okay. Okay, so here you are asked to find the modulation index. Okay, so that is nothing but AM divided by AC. This is the modulation index, and if you get the percentage, you can get the modulation percentage. So here it is 10 divided by 5, that means 1 by 5, that means 0.2, the mu is equal to 0.2. Okay, so here mu is equal to 0.2, and the modulation percentage is 20. Okay, so you can use that one. Okay, so okay, now you are asked to draw the full AM spectrum. Okay, so you are asked to draw the full AM spectrum. Okay, so I have explained you what are the what is the difference between the waveform and the spectrum. Okay, waveform is a time domain signal. Waveform is the time domain signal, time domain representation, time domain representation of the signal. Okay, signal. So that is the waveform, and this is the thing we have find. This is the waveform actually. Okay, these are the waveform. This one, and this one. Both are same. Okay, all are same. The three expression are same. This is also the waveform, and this is also the waveform, and this is also the waveform. So you can write it anyway. Okay, but what is the spectrum? Spectrum is frequency domain representation. Frequency domain representation. Okay, of the signal. Okay, so here you are draw the signal with respect to time voltage variation like this. Okay, and here you are write the voltage variation or power variation with respect to frequency. Okay, so different frequency component has different power, so you will get this kind of power. Okay, so that is the okay. So how to draw the AM spectrum here? Okay, so how to draw the full AM spectrum? So it is also very easy. Okay, so spectrum means okay. So you have to find the actually to find the spectrum. Okay, the the, the normal way is okay. You have to put the Fourier transform for this signal. Okay, you have to find the Fourier transform of this signal. Okay, so we have the XMT. Okay, XMT, and you have to get the Fourier transform of this signal. Okay, so you will get the value. Okay, so you will get the spectrum. Okay, but uh, some student haven't done the signal and system yet. Okay, so I'm not going to talk about the Fourier analysis. Okay, so if you interested, you can see my other. I have uploaded some video. You can check them. Okay, so here we will try to find our spectrum. Okay, it is also approximately correct. Okay, without uh, converting to a Fourier domain. Okay, without using the Fourier analysis, we will try to find the spectrum. Okay, so actually we can find it. Okay, so how we can find it? Okay, so that may be 100% correct. Okay, that may be not 100% correct, but it is an idea. Okay, so you can see that this is the waveform. No? So this is the waveform, and you have separate frequency component here. This is one frequency component. This is another frequency component, and this is another frequency component. Okay, so these are frequency component. Okay, sine and cosine wave. Okay, so if I draw a graph like this, okay, and if I now I am going to draw the power. I will going to draw the power with respect to the frequency, hertz. Okay, so power with what? Okay, not voltage. Okay, I will take the power. Okay, because voltage is changing here. No? So you can see that this is a uh, sinusoidal wave. Okay, so the voltage is changing. Okay, so but the power is constant. Okay, so if you consider this one, this frequency component, this is the power of that one. If you use this frequency component, this is the power of that one. If you use this frequency component, this is the power of that one. Okay, so you can see that this is the highest power. This has the highest power. Okay, so these are very low power. Okay, so this is the carrier signal, actually carrier component. Okay, it has the highest power. Okay, so you can see that there are three frequency components. Okay, so if I mark the three frequency component, we have the carrier component omega c, and we have another one omega c plus omega m, and we have another one omega c minus omega m. Okay, so these are the three frequencies we have. Okay, so this frequency has AC square by 2 power. Okay, so it has AC square divided by 2. This is the power of the carrier current. Okay, so it is look like this. Okay, so what is the power of this one? So the power of this term is AM square divided by 8, and the same power is there for this one. Okay, so we will get like this. Okay, we will get like this. Okay, actually this is the Fourier, this is the uh, frequency spectrum. Okay, frequency spectrum. Okay, but please go to my if you can visit, if you go to my other video, you can see that if you put the Fourier transform, you also get negative component also. Okay, so you will get some negative component also like this. Okay, so you have minus omega c here. Okay, minus omega c here. You have here mm, omega m minus omega c, and here you have minus omega m omega c. Okay, so this part also you will have. Okay, and this is the negative component. Okay, it is come due to the, it is come because of the Fourier transform. Okay, if you put the Fourier transform, you will get this one also. Okay, 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 but this is a negative one. Okay, so this is, so we can see that this is the imaginary one actually, because if you use a spectrum analyze and check the uh, spectrum, you will get only plus sign. Okay, actually you will get this kind of one. Okay, here you have this kind of one. Okay, and here you have I1, and here you have I1. Okay, actually you will get this kind of spectrum if you use a spectrum analyze. Okay, if you use the spectrum analyze and check, you will get this kind of spectrum. Okay, this kind of spectrum. This is the actual spectrum you get. Okay, and you can't see this imaginary part. Okay, so if you draw this one, you can give the, we can give you the full marks. Okay, so that is it. Okay, so I think now you can do this one also. Okay, you can do this one also. Okay, okay, now draw the waveform. We have already do that one. Okay, we have already do that one. Okay, we will already do that one. Okay, so we know that how to write the waveform. Okay, so we know that. Okay, we know that this is time. Okay, and we have the AC. Okay, and here we have minus AC. Okay, minus AC, and here you have plus AM plus AC. This AM is the amplitude of modulation, okay, modulating signal, and here you have AC minus AM. Here also you have minus AC plus AM. Okay. And here you have minus AC minus AM. Okay. So here your voltage, your signal is changing like this. Okay. And here also your signal is changing like this. Okay. Like this. And so this is actually the waveform. Okay. So we will get this kind of waveform. Okay. This kind of waveform. So this is the waveform. Okay. So what you have to do that you can put AC, AC AM, AM plus AC. Okay. So as I can remember, AC is 50 and AC is 10. Okay. So so you no need to write the frequency very well. Okay. So but if you have to correctly mark the amplitude levels. Okay. So this will be 40 and this will be 50 and this will be 60. So this will be minus 40, this will be minus 50, and this will be minus 60. Okay. So if you correctly mark this, uh, amplitude level, you can get the mark. Okay. And you can see that. Okay. So we know that mu is equal to AM divided by AC. AM is 1 and AM is 10 and AC is 5. So you will have 0.2. That means mu is less than 1. Okay. So at that time you will get this kind of envelope. Okay. So this is called the envelope. So you will get this one. Okay. And we have already discussed that it's if AM divided by AC. If AM equal AC, your mu will be 1. Then you will touch this. Okay. Then you will touch this x-axis like this. Okay. So your envelope will touch the x-axis like this. Okay. So here you have this kind of. Okay. Okay. And if mu, okay, and if mu is, you know that AM divided by AC, and let's say that AM is greater than AC. Okay. So you will, okay, so you will have mu is greater than 1. Okay. At that time, this will cross this point will cross the x-axis or zero axis. Okay. So you will get this kind of. Okay. So I will write it here. Okay. So you will get somewhat like this. Okay. So you will get somewhat like this. Okay. So you have a part here. Okay. Actually, this is a distortion. Okay. So if we get this kind of signal, it cannot detect it. Some information can be missing. Okay. So this is not the proper way. Okay. So here, these situations are not the proper way. Okay. Because some information can be lost here. So this is called over-modulation. Okay. It is not talking. Okay. So we like to this one. Okay. So the AM, that means AM should be less than AC. The carrier amplitude should be high. Okay. Than the signal amplitude, our modulating signal amplitude. Okay. Okay. So that is it. Okay. And so so actually last time we have developed a MATLAB program. I think you can remember that. Okay. This one. Okay. You have developed it one. Okay. So actually this program is correct. Okay. So I think you can understand this. Okay. So this is the amplitude of the modulating signal. This is the amplitude of the carrier. This is the frequency of the modulating signal, and this is the frequency of the carrier. And this mu is the modulation index. So we can define it like this. Okay. So we are going to plot the waveform. Okay. So we are going to plot the waveform. Okay. And we have, okay, and we have like this one. Okay. And we have so we are going to plot the waveform. Okay, so this is our modulating signal, information signal, and this is our carrier signal. Okay, so I have write them in as, okay, in the same way. Okay, so we have a t here. Okay, and other also we know. Okay, but we need to define this t. This t is the independent variable. Okay, so we define the t like this. Okay, so we will get some t values. Okay, and I think we have separately plot the carrier signal and the information signal. Okay, so if I separately plot them, okay, so this is the information signal. Okay, so I will comment this. Okay. So this is our message signal. Okay, and if I draw the carrier signal, okay, so I will draw the carrier signal in the same plot. Okay, so this is the carrier signal actually. We have to put the hold on, otherwise uh, the both are not drawn in the same graph. Okay, and if I, okay, so you can see that this is our amplitude, sorry, modulating signal, and this is our carrier signal. You can see that the carrier signal frequency is higher uh, than this frequency. Okay, and but the problem is there. What is that? Okay, so you can see that carrier signal amplitude is, sorry, carrier signal amplitude is lower than the modulating signal amplitude, information signal amplitude. Okay, so you will not get a correct uh, correct mm, waveform. Okay, distorted waveform, over modulated waveform you will get. Okay, and if so we can put a lower value. Okay, so I set it as 20. Okay, so it is less than 50. Okay, so in the same manner I will put it as 10. Okay, okay. So now if I go, okay, so this is my information signal and this is a carrier signal. Now the conditions are okay. Okay, now this is our modulated signal. Okay, so you can code it very easily. Okay, you have to code the same thing. Okay, but uh, you have to remember that when you are putting, if you are putting this mu, okay, if you are putting this mu, you need no, you can't put the amplitude. Okay, so here the mt is am cos omega ct, omega mt. Okay, so am is there and am divided by ac. Okay, so am divided by ac, the mu is here. Okay, so but I didn't put the mu here, but already mu is here. You know that. Okay, because this mt is equal to am cos 25 fmt. Okay, so am cos 25 amt, that means am divided by ac is there. That means mu is there. Okay, mu mt is there. Okay, and ct is here. Ct has this ac value also. Okay, so you have, okay, uh, ac cos omega ct also. Okay, so this is the correct way to write the signal. Okay, so so if you plot, if you go this one, this modulated signal. Okay, now I will remove this one. Okay, I will remove this one. I will comment. Okay, and if I write the modulated signal, so this is the modulated signal. Okay, XMT. Okay, so you can see that we have a modulated signal. Okay, so this is our modulated signal. This is a correct signal actually. Okay, so we try to draw this, draw the, uh, we try to draw the envelope. Okay, so when we are drawing it, okay, we can't properly do it if we are going to draw the uh, envelope by the hand, so you can't properly draw it. Okay, so if you want to, if we can try to plot, we can uh, try to, draw the envelope in the MATLAB, okay? So I have already told you what is the procedure, okay? So if you look at this value, look at this one, you can see this is our carrier signal, okay? So envelope is made using the information signal, okay? So this is nothing but the information signal, okay? So this envelope is nothing but the information signal. So this is the information signal, actually. Information signal. But it is shifted upward. It is shifted. Actually, it is shifted by AC. Okay, it is shifted by AC. So your if you shifted your message signal, so this is the message signal, and if you shifted it by AC, okay, if you shifted it by AC, okay, so I have put here plus AC. That means I am shifting it. Okay. So it is just like I give a DC offset. Okay. So I have shown, I have told you to see it in the using the signal generator and oscilloscope. I think now you have the idea about that. Okay. So you have checked it. Okay. What happened when we give the DC offset to the signal? It is shift up or down. Okay. So if you give them plus DC shift, it go up. If you give the minus DC, it go down. Okay. So you already know it. Okay. So if I run this, so the hold on it should be there. Okay. Okay. So you can see that this is the upper envelope. Okay. So it is sorted. And if you need to find uh, the low envelope, so you can see that it is also shifted. The waveform is shifted downward. Okay, downward by AC, downward by AC, but it is not only shifting. Okay, the signal is like this, but it is downward. It is shifted to down. It is like this. Okay, but this one is not like that, no? It is inverting. Okay, it is inverting like this. Okay, it is shifted down and it is inverting like this. Okay, it is inverting. Okay, so what you have to do, you can shift it by minus AC and you have to invert it. That means you have to multiply by it using minus. Okay, so if you multiply your signal by minus 1 and add minus AC value, you will get this envelope, this wave here. Okay, so it is actually the lower envelope. Okay, lower part of the envelope. Okay, so I will use this. Okay, I will use this, and if I put here minus AC, okay, so it should be the minus. Okay, so I have to remove the hold on here also. And if I run, okay, so you can see that the envelope is there. Okay, actually we in the real signal we doesn't have this envelope. We have only this carrier frequency with change in. Okay, so this is actually the transmitted signal. Okay, so I just draw the envelope here. Okay, okay. Okay, then, okay, so now you can see what happen if we equal AM is equal to AC. Okay, that means mu is equal to 1. Okay, so now your envelope touch the zero axis. You can see that. Okay, so and also you can see that if you somewhat higher your AM, okay, so those are all modulated signal. Okay, so you can see that it will cross, and this part you can see that it will generate this part. Okay, so I think that that is enough. Okay, and I hope now you can do this question by yourself. Okay, okay, so this kind of question will come to your exam also. Please try to work out this one and try to uh, familiar with this one, okay? And also we have to find the bandwidth, transmission bandwidth, okay? So the transmission bandwidth is the full spectrum, okay? So normally that is the uh, definition. There are many definitions for the bandwidth, okay? So here we are asking the full uh, frequency range we are transmitting, okay? So this is the minimum frequency range we are transmitting, that is omega c minus omega m. This is the minimum one, okay, minimum frequency. And this is the maximum frequency we are transmitting, that is omega c plus omega m, okay? So the bandwidth, actually the bandwidth is nothing but the maximum frequency minus minimum frequency, okay? So what is the maximum frequency? That is omega c plus omega m, minus minimum frequency is nothing but omega c minus omega m, okay? So you can see that omega c cancel out, and plus this is minus minus, and you will get 2 omega m, okay? So this is the bandwidth, okay? So this is the bandwidth, okay? So I think it is okay. Now I think you can work out uh, uh, you can work out uh, amplitude modulated signal question if I given, okay? So just practice, and I have given some other examples also, so you can practice and you can sharpen your knowledge, okay? Okay, thank you.